Okay. Gut. Also, willkommen zur Vorlesung. Was haben wir gelernt vor 2 Tagen? Also wir haben den Begriff der Gröbner-Basis. Vielleicht wiederhole ich noch mal kurz die Definition. Also wir arbeiten im Polynomring und wir fixieren eine Termordnung. Okay, it's English, sorry, I should speak English. So we work in the polynomial ring, we fix the term order. And then let's say we have a finite set of polynomials. I call the finite set G. Finite. So I recall the definition of Gröbner basis. So what does it mean for G to be a Gröbner basis? So the definition was as follows. We are interested in the so-called leading ideal, which I denoted with LT, leading ideal. So this is the leading ideal. Of the ideal generated by G. So I recall you just for any non-zero element in this ideal, you take the leading term. And the monomial ideal generated by all these terms, this is the leading ideal. And now the beautiful situation is if this is exactly the ideal generated by the leading terms of my set G. Okay, it's clear that the right-hand set, this one is always contained here. This is trivial, but if there is equality, we have a Gröbner basis. Okay, so we learned there is a criterion by which you can effectively test whether you have a Gröbner basis. So this involves the concept of the S polynomials. So for any pair of polynomials in the set G, you form the S polynomial. Then you reduce sigma G, for instance, using the division algorithm, and you check whether it gets 0. And if this is the case for all pairs, then you have a Gröbner basis. And this is if and only if. Okay, and once this has been observed, it's quite easy to come up with an algorithm to compute the Gröbner basis. So this is Buchberger's algorithm. Maybe I don't repeat it here. It was quite simple. Okay. Right, so this is the concept of Gröbner basis. But now let's talk about uniqueness. Okay, is a Gröbner basis unique? I mean, I always assume the term order is fixed. But very easy to see that certainly is not unique. I mean, for instance, we can do, okay, now let's talk about uniqueness. Uniqueness.
Can I ask a very short question about the Buchberger's algorithm?
Yes.
The thing is, there we didn't really order anything in any step, right? So we can do.
You picked a pair, right? I didn't say. I mean, actually, the order in which to pick the pairs can affect the speed, of course, but I didn't specify it. So in a way, it's like, if you want to say, it's like
not the order of pairs, the order of division, because that isn't yet a Gröbner basis, and the order of division.
Correct. So okay, my writing is a bit sloppy. So actually, then you should replace this set of polynomials by a sequence of polynomials. You order it, and then it's defined. I know I'm a little bit.
Okay, I understand. So, and everything that is added in at some place, for example, at the end of the sequence, and then it will work. Yeah, of course it will work.
Yes.
Okay.
Yes, yeah.
Okay.
Okay. Right, because if it turns out to be right. Yeah, but it's the question is legitimate. So how about uniqueness? So let me start with a very easy observation. If you have G, if it's a Gröbner basis, I just try G basis to save some space for, say, for some ideal I. And then you take a superset. Let's say G is contained in G prime, contained in the ideal I, and this is finite. Then trivially, this G prime is also a Gröbner basis for I. Yeah, I should close this. Yeah, I mean, you add more elements, the more the better. Okay, it's certainly a Gröbner basis. So this, okay, once you noted that, then you come up immediately with the concept of a minimal Gröbner basis. So what does it mean, minimal? It's a Gröbner basis for the ideal, but if you remove an element of it, it will not be a Gröbner basis of the ideal anymore. Okay, so let's say G is minimal Gröbner basis. If, okay, G is a Gröbner basis. And okay, for all proper subsets, G prime of G, proper, G prime not Gröbner basis, okay, of the ideal generated by G. Okay, you cannot remove any terms. Okay, so then it's very easy to characterize what this actually is. So let me write it as a lemma. The lemma is almost obvious. So let I be an ideal. And G a Gröbner basis of I. And then I have three conditions and they are all equivalent. So one is G is a minimal Gröbner basis for I. Okay, that's what we want to study. The second is now more concrete condition. Okay, pick any element G of capital G, remove it. Okay, then we must have that the leading term of G is not in the monomial ideal generated by the set G after removing the element small g. So if you remove from G small g, look at the monomial ideal generated, you get some, no, the G is, leading term of G is not contained anymore. Condition 3, LT of G, yeah, you remember this notation, I think right, this is just the collection of the leading terms of the polynomials in G. This is a minimal system of generating of the leading ideal. Is a minimal system of generators of the leading ideal. So let's do the proof yourself. It's very easy. So this lemma shows this minimal Gröbner basis actually only talks about the leading ideal of I and the leading terms of G's. Okay. And we note that if I have a monomial ideal, then there is a unique set. There's a unique minimal set of generators. So, minimal set, minimal set of generators of monomial ideals is unique. Okay, therefore, now we see, what can we see about uniqueness? I mean, if you have two minimal Gröbner bases, they must have the same cardinality. Okay. Minimal Gröbner basis has same cardinality. Because the collection of leading terms of such a Gröbner basis is a minimal system of generators of the leading ideal, and this is unique. Okay, let's do an example. 2 days ago, we had Okay, we had an example where we actually carried out the Buchberger algorithm by hand. And so what in this example, I started with two polynomials. F1 was x cubed minus 2xy. I just put it down again. This was the input plus x. And we had the graded lexicographic ordering. And then we did the computation. And then we came up with this. Just reproduce it. And I say we had graded lexicographic ordering. So let me underline the leading terms. There's this, and this, and this. And here is only one, and this. These are the leading terms. So this was the result of the computation. Then now if you think about minimality, then we see that the F1 and the F2, we don't need. Okay, because here F1, it has x cubed as a leading term. But x cubed is just a multiple of x squared. So the F1 we can kick out. The F2 has x squared y. That's a multiple of xy. So the F2 we can kick out. And the others need to stay. So we see F3, F4, F5 is minimal Gröbner basis. Okay, I cannot, if I have this, I have x squared, xy, y squared. I need all of these three terms, okay? As soon as I remove one of them, I will get something smaller. So this is a minimal Gröbner basis. Okay, and I think it's clear how to compute from a Gröbner basis a minimal Gröbner basis. Maybe clear how to compute a minimal Gröbner basis from a Gröbner basis. I mean, okay, it's just about the divisibility condition of these leading terms. I think there's not much to say here, but right. But the minimal Gröbner basis, they are not uniquely determined. Here is a very easy example. Minimal not unique, not uniquely determined. So I give a very simple example. So let's say in the above case, I add to F3 a multiple of xy. The others I keep. Okay. Alpha is any field element. So, and I claim this is also a minimal Gröbner basis. Okay, so why? Let's first check that this generates the same ideal as this. But you see, the xy, I add a multiple of xy, but the xy is up to a factor, is the f4. So actually what I add here is a multiple of f4. So clearly, if I add to f3 a multiple f4, the ideal is the same. So I have the same ideal. And then, I mean, if we check minimality, but then for checking minimality, we only have to look at the leading term. So I only changed here something. So I add to F3 alpha xy, but it doesn't change the leading term. F3 plus alpha xy still will have this leading term. So it's clear. I mean, it's also a minimal Gröbner basis. So there are many. So we want to have another notion which is unique, and this is the notion of a reduced Gröbner basis. A reduced Gröbner basis will be unique. Okay, so let's define what would that be, a reduced Gröbner basis? So in this example, what we can do, we take this. And then, I mean, we can get rid of this alpha xy by making a division with remainder by f4. Okay, if we divide this by this will go away. Okay, and this leads to the notion of reduced Grabner basis. All terms, okay, let me write it. We want to have reducedness of all elements with respect to the other elements in the Grabner basis. The definition. Okay, a reduced Grabner basis of ideal I is a Grabner basis of I such that, okay, this is the interesting condition. Take any polynomial in G, and then I want that G is a normal form modulo the remaining elements. So if I remove small g from the set, yeah, I cannot reduce the element G further modulo the other elements. Okay, and the second condition is quite boring. I just require that for, yeah, the leading coefficients of all elements of G is 1. This is just normalization. Okay, so this is a definition of a reduced Grabner basis. Okay, so in the example, okay, it's, I think, pretty obvious. Okay, it's another, right? Is it that example or is another? It's the same example up to sign. So let's say x squared minus alpha xy, y squared minus 1/2 x. So when is this reduced? Let's see. Okay. Leading terms, again, I assume graded lexicographic ordering. If and only if alpha equals 0. Okay. Okay, because this guy, of course, this I can reduce modulo the others. But if this is gone, okay, there is no way to reduce. So let's see, like I have y squared minus x. Is it possible to, is this a normal form? Well, let's check. Why is it a normal form? Okay, let's try to divide by this. Okay, but this here, the leading term is x squared. X squared doesn't divide y squared. X squared doesn't divide x. Same here. Xy doesn't divide y squared. Xy doesn't divide this. Okay, so I checked. It's reduced when alpha equals 0. Okay, so now this is also quite obvious, but okay, once you have a, let's say you have a Grabner basis, then you get the minimal Grabner basis. That's very easy. And from the minimal, by a little computation, you get a reduced one just by doing division with remainders, but maybe let me write it as a routine. So we have this little algorithm. Okay, let's do it. So little algorithm. So what does it take as input? A minimal Grabner basis. Let's call it f of the ideal I. Of course, it's understood the term order is fixed, and the output is a reduced Grabner basis G of the same ideal. Okay, begin. When you see when I write begin, I'm quite old, so my first programming language I learned was Pascal, you know, many decades ago. Very old-fashioned, no Java and so on. So okay, I initialize G this to F. Then for all G in F, let's do the following. Okay. If. Okay, if so, also I studied in Zurich and Pascal was developed in Zurich, so it's quite okay. Okay, so if the term set of G intersect what? So now I take the monomial ideal of the leading terms of capital G minus G, so I remove that and then I check. Okay, is it empty or not? If it's not empty, then I can reduce. Then I make division with remainder. So I take G, reduce. Now again, I'm sure Lev will ask. I'm again sloppy, but you understand I want to be simple on the notation. So, right? Okay, that's okay. I call this H. You have ordered everything, then it's unique. Else, I say H is just G. And this then end, and if. And then I update my set G. So what I do is I remove small g and replace it by the H. What? Okay, little pedantic thing I have to normalize. So I take here H, but divide it by the leading coefficient of H. So the leading coefficient will be 1. Okay, and that's it. So end of 4. Oh, sorry. And 4 and end of everything and begin. Okay, so that's very easy. And I mean, you can yourself, okay, convince yourself that this algorithm works correctly. I am not going to prove it. It's very easy. Algorithm works correctly. And also, we don't have to worry about worrying time, the running time. There is no loop in it, nothing. Okay, there's no problem at all. Okay, so, or is there any question? No question. Okay, simple enough. So now I have this nice little theorem saying that reduced Gröbner bases are unique. So every ideal I in the polynomial ring, let's maybe write it explicitly, with respect, okay, has exactly one reduced Gröbner basis with respect to a chosen term order. Exactly one. So this is nice. Okay. No, so right. Okay, let's prove it. So the existence forms via algorithm, existence by algorithm. Okay, the algorithm shows existence. So it's all about the uniqueness. So let's prove the uniqueness. So I assume I have two reduced Gröbner bases. Let G and G twiddle be reduced Gröbner basis of I. I want to show they are equal. Okay, I will show G is a subset of G twiddle, and then by symmetry, I get equality. Okay, so first step, I just use that G and G prime are minimal Gröbner bases, so I see the set of leading terms, LTG and LTG twiddle. These are minimal systems of generators, minimal systems of generators of the leading ideal. So they are equal. Okay. This is the minimality of the minimal Gröbner basis. If you just look at the what happens in the leading terms. So for if I have a G in G, there exists a G twiddle with so such that the leading term of G twiddle is the leading term of G. Okay, so maybe move it down. Okay, good. So now I want to show G must be equal to G twiddle. So, okay, since now I note that the leading coefficient of G and the leading coefficient of G twiddle, they are both 1. So they are equal because both are reduced Gröbner bases. Okay. So if I subtract, what happens? If I subtract, if I form G minus G twiddle, there is a cancellation. The leading term, they have the same leading term, both coefficient 1, so it goes away. So the term set of this is a subset of a union of terms of G with unions of term of G twiddle, but the leading term of G is not there anymore. This has gone away. This one I removed by the subtraction. Okay. So now let's, okay, little claim. Little claim. I claim the term set of G minus G twiddle is disjoint from the monomial ideal coming from generated by the leading terms of G. Let's prove. Check this. Okay. So let's check the, okay, I do every little step. Let's show this claim. Why is this? Otherwise, there is some term here of the difference G minus G twiddle, which lies here in this monomial ideal coming from the leading terms of G. Then without loss of generality, I can assume T is a term of G because it's a completely symmetric situation. T or G twiddle, it doesn't matter because I know, I mean, they have the same, okay, these two are equal. So without loss of generality, I can assume that. Right, what do I want to say? But T is different from the leading term of G. Yeah, because I know, I mean here, the terms of the difference, you know, this is not contained anymore. So it must be different. Okay, so now since now I use the reducedness. So the term set of G is disjoint from this. So this condition, you know, characterizes the reducedness of G. So I have this. So I see that, so maybe the arrow is better to put it here. So what do I see? The leading, so I conclude the leading term of G divides T. Okay. Yeah. So the only, yeah. So maybe I'm a little bit going to a too much detailed level, but right. So, but then, I mean, T was a term of the polynomial G, so they must be equal. This is a contradiction. Okay, so maybe I gave too many details. I don't know. I just wanted to be very formal, but I think there is nothing. Okay, and now from the claim. So this claim expresses that this is a normal form of G. So the claim says G minus G twiddle is a normal form. Mod G. And okay, but on the other hand, G minus G twiddle is in the ideal, so it must be 0. Okay, if you have an element in the ideal generated by a Gröbner basis, it's a normal form, must be 0. So therefore, G is G twiddle, and we showed. So G was arbitrary. What we actually showed is this inclusion. And by symmetry, we have equality. Okay. Are there questions on that?
Maybe one little question. I didn't fully understand at the beginning. We said that leading terms of G, leading terms of G twiddle are minimal systems of generators. So they are equal. Could you explain why?
Right. Okay. Right. This was actually used it before. Then we just focus on monomial ideals, right? So we know monomial ideals are finitely generated. That's Dixon's lemma. But we also know that minimal systems of generators are unique. So I think it appeared earlier. And how did I formally prove it or not? So it had to do with this picture. Okay, I make a picture like in N2. So if I picture a monomial ideal, so meaning that a monomial in 2 variables will be a pair of natural numbers, which I can represent as a point in N2. So I have a couple of points, okay? Combinatorial object. And what does it mean to be an ideal? It means whenever you have a point, the whole this whole quadrant must be contained in the ideal. So all of the points here must be in it. Now, if you reason how, and you know also we proved it is finitely generated. So the only way this can happen is the picture is you said you always have such a staircase, okay? And the monomial ideal consists of the points above the staircase. Now, this is not a formal proof, but it's a picture. So I think you will understand. And then the minimal generators are at the corners, okay? All of these things you must have, okay? If you remove one of them, you cannot get the whole thing, okay? And on the other hand, this is enough. So this is like a pictorial proof, not formal, but pictorial, why it's unique. But I think, I don't remember whether I gave a formal proof of the uniqueness or not. I have to look back in my notes, but it's nothing difficult.
Okay, thank you. Then
okay, you see.
Again.
So these are the actually, yeah. Okay. Other questions? Okay, doesn't seem to be the case. So good. Then let me. Nice is. Let's see the relation to linear algebra. What is linear algebra about? I mean, structurally speaking, okay, if you are not a numerical analyst, you're just an algebraist, we just look at linear polynomials. Okay, linear polynomials, their solutions and so on over an abstract field. But now in this context, we also look at nonlinear polynomials. But let's go back. what does this concept of a reduced Gröbner basis mean in the very special case of linear polynomials? So we will encounter familiar notions from linear algebra. So let's do this example. I think it's quite instructive to understand what this is all about. Connection to linear algebra. So I encode my family of linear polynomials by a matrix and a vector. So I have a matrix A over a field of format S times n plus 1. Okay, this is the whole thing. Then, right, then I look at the polynomials Gi, Aij, Xj, J goes from 1 to n, plus a constant term, this is the Ai n plus 1. Okay, that's right. And this, how many? I have S polynomials. Okay, just the matrix encodes this. Then let's use the lexicographic order where the variables are ordered this way. So the x1 is the largest by convention. Okay, so now let's see. When is this sequence of the G's a minimal Gröbner basis? Gröbner basis. Of course, Gröbner basis of the idea generated by it. I don't think I have to write this. So what do you think? Okay, let's.
Shouldn't it be up to GS?
Yes, sorry?
Shouldn't it be up to GS?
This is correct.
And my guess is that if the Aij are, if the column vector I is linearly independent.
The column vectors, you think of the column vectors. Okay, let me make a picture. Column vectors linearly independent.
Maybe if
No,
A is
I don't.
in row echelon form.
Yeah, right. Now, okay. Regarding the first answer, now you must notice you said independence of columns, but that's an invariant notion. A notion, it does not depend on the choice of a term order. While the Gröbner basis always will depend on the choice of the term order. So it's rather a combinatorial combination than it's not an invariant condition. Your answer, Larissa, is correct. That's exactly after, okay, after permutation of the rows of A, because the rows, I mean, the permutation of the rows corresponds to permuting the G's. A is in echelon form. So I can make a picture. So this is supposed to be A. So what is this echelon form? Maybe I have, you know, just zeros here, nothing happens. But then here, okay, here I make a cross, it's a non-zero element. Okay. And then there is, you know, something. Okay, I just maybe it goes like that. So here everything is zero. At the corners I have the non-zero elements. Okay, and above, for the moment, I don't care anything. So this is this echelon form. Let's check. Why is that? Let's assume A looks like that. So why do we have a minimal Gröbner basis? So why is it minimal? Yeah, I mean, we look at the terms. The leading terms here, these are the variables, okay? Right? And these are distinct variables, right? So assume for a moment, just for a second, assume I had maybe here I also had an element. Okay, here there would be something non-zero. Then x1 would appear twice as a leading term. Okay, so I don't have minimality. So once I have this, here I must have 0. Okay, cannot appear anymore, right? And then you go on. Okay, so in the second, etc., etc. So this is actually, it's easy for, I mean, formal proof of that is quite easy, and I'll leave it to you, the details. So this is a concept we know very well from linear algebra. Now let's figure out what additional conditions are required to have a reduced Gröbner basis. So maybe here, reduced. If and only if. So what do you think? What will that be? By using, yeah,
an
okay.
uneducated guess would be if A is in reduced echelon form.
Yeah, okay, what is reduced echelon form? Because I always forget these names.
I would say it's the red entries are normed to 1, and above the red entries are zeros.
Correct. And this is called reduced echelon form. How nice. Correct. That's exactly. So I, again, try my artistic qualities. Writing, okay, it's a bit, okay. So how many corners I have? Zack, zack, zack. 1, 2, 3, 4, 1, 2, 3. Okay, it's good. Here, let's put it maybe in red. It should be 1, correct. And then below as before 0, but what is additional, maybe, right. So here I also will have 0 and 0 and 0 and 0 and 0 and 0, and otherwise anything. I think this is anything. So this is reduced echelon form. I wasn't sure whether it is called reduced echelon form, but I guess it, if you say it, it will be like that.
Or reduced row echelon form, I think.
Okay, because you can even reduce more.
No, but I'm not sure. I always met row echelon.
So this is also row echelon form, actually. Probably I should say row echelon form.
Yeah, exactly.
Okay. I should teach linear algebra, then I would remember the namings. Okay, so this kind of really shows Gröbner basis. Well, that's that. What do we know from linear algebra? What is the algorithm in linear algebra to do this computation? Is Gauss elimination. So now Buchberger's algorithm is kind of, it's like Gauss elimination, but it's much more complicated, much more involved. Okay, I mean, meaning that the algorithm is not that complicated to state, but if you really want to understand what's going on with this algorithm, very complicated in a way. Say, for instance, a question that I didn't address at all, and I don't dare to enter it in this lecture, is about, I mean, how big can this Gröbner basis be? Okay, you start with a harmless looking system of polynomials, choose your turnover, and then you get a monster. So this may happen. So actually, one can show that the size of the Gröbner basis can be doubly exponential in the number of variables. Can you imagine that? Doubly exponential. So it's quite okay. but this doesn't belong to a, rather this should be discussed in a lecture on computations in commutative algebra, not in a lecture focusing on the basic aspects. Okay, so now let's talk about applications. So, right. So now when we assume we are on the lucky position, we have a Gröbner basis and it's not that enormous, then we can answer all kinds of questions. Okay. Okay, also in the chat, it was left as an exercise. Thank you. So 2.5, elimination. And you remember, I think we had this already a little bit on an exercise sheet. Now we will understand it in more detail. Elimination is a very classical topic from the 19th century. So let me start with the definition. What is an elimination ideal? And then there will be the geometric explanation. So I have an ideal I in my polynomial ring. An ideal. Then I pick some natural number between 1 and n. Okay, and then I define what is the kth elimination ideal. The kth elimination ideal. Okay, ik. So this will be in the polynomial ring only depending on the last m minus k variables. So on xk plus 1 up to xn. Right, x1 up to xk do not appear here. So is defined as, okay, what we do, we intersect the ideal I with this polynomial ring. So we just collect, okay, we just look at the polynomials in I, which only depend on the last m minus k variables. This is the elimination ideal. Okay, there are two things. One is, what does this mean? And the other is, how do we compute it? Okay, how to compute it, we'll see with Gröbner basis, but let's first talk a little bit about what this means. So there is always this dilemma that the meaning, like the geometric meaning, requires some basic understanding of notions of algebraic geometry, which I understand were discussed in the exercise session. So I will go through it quickly without too many details. Okay, geometric meaning. Geometric meaning. So, okay, I'll be brief, but actually, yeah, what is this? There is the zero set, V of I. Set of points, let me call xi and write xi instead of x because x is a variable, xi in k to the n, such that for all f in I, f of xi equals 0. So this is the zero set of the ideal I. Okay, some people say, yeah, it's an algebraic set and so on. And then I have, on the other hand, if I have a subset W of k to the n, I define, so maybe this was a definition, the vanishing ideal I of W is defined as the set of those polynomials, so I just write kx to save space, which vanish at all points of W. So this is called the vanishing ideal. Of W. So these are actually very important definitions. They are just here, kind of, okay. The lecture is on commutative algebra, so they are more like for illustration. And, okay. Okay, so now, okay, one says W is Zariski closed. So W as a subset of K to the N is Zariski closed. If and only if, that's also a definition. It's the zero set of an ideal. So there is some I such that W is the zero set of I. So this Zariski, was it in the exercises or not? I think so. Or
Yes, it was.
it was, okay. So Zariski closed. So this leads to the notion of the Zariski topology. So in a way, very useful, but also kind of, okay, gewöhnungsbedürftig. I would say German takes some time to get used to it. It's a topology, but it's kind of strange. It's not Hausdorff and so. But still many things work. And then if W is Zariski closed, then we have, okay, I first take vanishing ideal and then zero set, then I get back W. Okay, this is a kind of easy, I say easy. It requires a little bit of thought, but it's an elementary argument, which I will not elaborate here. Now, the interesting thing is, suppose now K is algebraically closed.
Excuse me?
Yes?
After the definition of Zariski closed, shouldn't it say W equals V of I?
All right. In my notes is correct, but I cannot even copy. Thank you. This was a typo. Thank you. Okay. So if K is Zariski closed, so for instance, think of complex numbers. Then, now this is the famous Nullstellensatz. This is the famous Nullstellensatz. So if I have an, if I have an ideal, then for ideal, let's call it J in the polynomial ring. What do? I have an ideal J. First, I take zero set, and then I apply I. Okay, you understand, this is a little bit confusing. I, on the one hand, right, you are not confused. I used I to write, okay. I have an I like an operator, and I, okay, let me change. This is really confusing. Let me change it. Let's call the zero set, the ideal, let's call them J. And this I is an operator, take vanishing ideal, and then it makes, okay, I don't want to change this. So then it will be more comprehensive. So there is, for an ideal, this we have, this is the radical ideal of things. This is the Nullstellensatz. Okay, Nullstellensatz due to Hilbert. So this is very fundamental. Okay, so, okay, I will prove it later on. Not now, it doesn't fit very well, but I prove it later on. For the moment, we can believe it. Okay, right. Right, one inclusion is trivial and the other is the difficult one. And if you are over the real number, it's all wrong. It only, I mean, it only works over algebraically closed field. So this is actually, so the point is here, and I think Marco has talked about it. So there is this dictionary. There's this dictionary between, on the one hand, you have algebra. On the other hand, you have geometry. Okay. And so you can go back and forth between, on the one hand, you have these ideals, say radical ideals. On the other hand, you have the Zariski closed subsets. And this gives a one-to-one correspondence, like radical ideals in such a polynomial ring. On the one hand, on the other hand, you have Zariski closed subsets. Maybe of k to the n, and if I want to be more precise, I should write here kx1 to xn, and then it turns out all kind of notions, say geometric notions, have an algebraic pendant and the other way around. So that's the basic idea of algebraic geometry. Okay. Okay, so this is okay. I want to use this to illustrate the meaning of the notion elimination ideal with. But maybe there are questions. I know I'm going now very fast, so maybe you have a question, a pressing question here.
Maybe can you like another notation for the elimination idea?
Another notation.
Yes, because I find it really confusing that the K is the field and also.
My God! For God's sake, how can I do this? Right. So is J, what is a good letter? L. Okay. You're right. The point is, in the English literature, people for field, they often don't say K, but they say F. Okay. Then there is not a problem. Good. Better? But the I leave because, okay. So otherwise I mess up everything. Okay. So, okay. Now the theorem. Of course, I cannot use the K anymore. But consider projection. So what is this projection? Pi L. It goes from K to the N to K to the N minus L. And I should say, I assume now the field is algebraically closed. Otherwise, everything will be wrong. I should say, assume K algebraically closed. Okay, I have this projection, and here I have to write n minus L. And what does it? It just forgets the first L coordinates. So if I have, maybe I should call them xi. Xi1 up to xi n is mapped to xi L plus 1 to xi n. Okay, forgets the first L coordinates. So I consider this projection. Let I be a polynomial ideal. Be ideal. Okay. And okay, put. Is it okay if I write V is the vanishing ideal, is the zero set of I? Okay. I could write W, but maybe it's not a good idea. I call this is the zero set. Then the point is, so what is, I have this ELF elimination ideal, okay? And I wonder, so this depends, this has polynomials depending only on XL plus 1 in Xn. And I want to understand the zero set of this. Maybe I realize, you know, it's more clever to put here W. Okay, I'm so flexible, I can do that. So I want to know, what is this? Okay, it must be, I mean, this thing will be here. Okay. So the guess, of course, the guess would be, it's the projection. But it's a projection of the pi L, but this is not 100% true. Then this equals the Zariski closure of the image of this. Okay, we'll have an, yeah, okay, we can do an example. Yeah, let's do an example. This is the statement. So means you do a projection, okay? You do a projection. You want to understand the image. I will immediately give an example now showing that the image is not always Zariski closed. Let's do this example. So the picture is this. It's the standard example. You have two variables. Let's call them X and Y. Then you have, I draw this hyperbola. So I have on the one hand, I have the ideal, principal ideal generated by X, Y minus 1. The zero set, which I drew here, is the hyperbola. Sorry. B. Okay. And then my projection, I project down. Here is my projection. It's pi 1. So the pi 1 goes from K2 to K. X1 is mapped, XY is mapped to Y. Okay. Then you see, so this is really a standard example. Then what is the image? Okay, the image of the W. So what do we have? I mean, we see we reach every point except this one. This one we don't get. All the non-zero points, all the X non-zero we get, of course, because we can just say Y is 1 over X. But this one we don't get. We cannot get that one. So the image is K minus the origin. Okay. Oh, good. Now, okay, we did not. Now let's. So this is not Zariski closed. Okay, I know we did not train Zariski topology, but why? What we are looking at this, we wonder, what are the Zariski closed subsets of that? Well, these are zero sets of polynomials. Take one polynomial. What is the zero set? Well, it could be the zero polynomial, then you have everything, all of K. But if it's not a zero polynomial, you get a finite set. And if you have more polynomials, even simpler. So we see the Zariski closed subsets are either K itself or the finite subsets of K. Okay, but K with zero removed is not finite. Okay, it's infinite. Okay, have an algebraically closed field. So it's not closed, Zariski closed. But what is the Zariski closure?
I have a question.
Yes.
If the set of polynomials is actually infinite, then why couldn't the set of zeros be infinite just as well?
Okay.
Or do
No,
we
this
assume
cannot
that
be.
the set of
No,
polynomials
you
is...
take, you have a, okay, you have an infinite collection of polynomials. But if in this collection you have at least one, if a non-zero polynomial in the collection, just one, then you are left with a finite
yeah, I
set.
understand. That was your first.
Okay. So what the Zariski closure, what do you think? What's that? Oh, I didn't know. You look at the smallest closed set that contains all of this, but there can only be K. Okay. Because if you get smaller, you have finite sets. Okay. So K is infinite. Okay. Okay. Note. Okay, I should write. Okay. I should write. Let me write this because I don't know what Marco will explain to you. Zariski closed subsets of K finite sets, finite subsets, and K. Note, K is infinite. Okay, then from this, we see that the risky closure of this equals K. Good. So now let's verify. We have this theorem. We can verify it. What's the elimination ideal? So I have the first elimination ideal. So what I do, I have I intersect with this. So which polynomials in I only depend on y? Well, it's only 0, nothing else. This is the 0 ideal. Okay, if it's non-zero, you have x in it. Okay. Right, and what is the vanishing ideal? Okay, not vanishing, sorry, I'm confused. The zero set of the 0 ideal, okay, interpreted in K is K. Okay, 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 interpret a subset of K. So maybe this is confusing, but I verified, okay, so verified theorem in examples. Okay, so sanity check. We looked at this simple example. We looked what does these things mean, and we verified that it's true in this example. Questions on that? I know this is a bit a difficult thing because I don't give many explanations on this geometry, on the geometry. So yeah, these are concepts that take time to digest. So, okay, no comments. So let me now prove this. Let's prove this. Okay, so elimination corresponds to projection. That's what I want to prove. Okay, the proof, I think it's quite short. So on the one hand, so what do I want to prove? Pi L, this is an L, sorry. So I first note the image of W under the projection is in the 0 set of IL. Okay, so why is that? I claim it should be clear, but so what do I, but maybe I need next, what do I take? I take a polynomial in IL. So this polynomial only depends, so maybe I can write it in a suggestive way, depends on these variables. The first L do not occur, okay? Now let's take a point in pi L of W. So what I have a point, psi 1, psi k, and KL, psi L plus 1 up to psi n. This is a point in W, right? Then the projection, so if this is called psi, so this is pi L of psi. So this is the here. So this is a point. So every point in the projection here looks like that. But what happens?
I'm sorry.
Yes.
Didn't we define pi L as the projection to K to the n minus L? So it should be the from L plus 1 to L.
Right.
Maybe I got it wrong.
No, you are all right. Okay. So what do I want to show? What I want to show, but okay, actually there's nothing to prove. It's all the notation. It's very difficult. So f evaluated at xi is 0. Okay. No, this I want to show. What do I want to show? Sorry, now I'm confused. What do I want to say? Let me think. I should say there's something I did not write. Okay, I should W. Okay, we should not forget the W is the vanishing ideal of I. Okay, so clearly if I have F in IL, so F is in I. If I evaluate at Xi, I get 0. Okay, but now you see this is the same. Yeah, so what else? Actually, there's nothing to prove. Okay, you see, so this is, I mean, the only thing maybe I can say, F, I don't have to write the first L coordinates. They are not there. In a way. So the upshot is, this is clear. Whatever, okay, I tried to explain because I felt an explanation was necessary, but I think this is clear, hopefully. If one figures out what do the concepts actually mean, I think there's nothing here. Check it out for yourself. And let's do the other inclusion, which requires a little bit of thinking. So for the other inclusion, okay, what do I take? I take a polynomial depending on the last variables, xl plus 1 with xn, such that f is in the vanishing ideal of the projection. So this is the small. So what I write. So now actually I look at this, but I want to prove this inclusion. Okay, so maybe I should write this because you are not used to these kind of arguments. I want to show this. I want to show this. So that's what I want to do. So how can I do that? Mm-hmm. Mm-hmm. Okay. Yeah, this is actually, I don't want to show that. This is wrong. I want to show, sorry, that this is Zariski closure of pi L of W. Okay, I have to go slowly. Otherwise you will not understand. Zariski closure. And what does this mean? Okay, this means the following. If you have a polynomial vanishing on this, then it must also vanish on this. This is the meaning of Zariski closure. Okay.
So it should be a minimal set that satisfies that
yes.
minimal with respect to inclusion, right?
Yes, so means that, okay, next means that any polynomial, but these objects are now subsets of k to the m minus l. So any polynomial f, depending only on variables corresponding to the subset I'm looking at. So now, depending on that, it means that any polynomial then which that vanishes here also vanishes here. In other words, yeah, okay. That's what I want to do. Okay, so it's clear that all of these little things, I mean, once you are familiar with the Zariski topology, it gets clear. But if it's very new to you, this takes all thinking. So I don't explain now everything, otherwise it takes too long. It's just about the geometric interpretation of elimination ideals. It's not a central topic of the lecture. But now let's do this. So, okay, so this is the plan. So I take a polynomial f that vanishes here. In other words, I can say it's in the vanishing ideal of this. And this k is an L, sorry about that. Getting confused with my L's, okay? Okay, then, my f actually vanishes on the W. Why? Yeah, okay, the f only depends on the last variables. So it doesn't see the other variables. So, I mean, this is completely the same. I mean, this and this are equivalent for polynomials only depending on the last m minus l variables. It's the same. Okay. So if view f as a polynomial in all variables. Okay. Now comes the, right, now I use the Nullstellensatz. Nullstellensatz. Okay. So, okay, I see my, okay, now I have the mess with the, I should have called the ILJL. It's a kind of a mess. You know what I want to do? Sorry. I renamed the ideal I by J because this is all, sorry for that. I didn't pay a lot of attention here when I prepared. Okay, so this is all of it is J now. Sorry. It will be better in the notes. Sorry, it's all J. This is on the video. It's terrible. Huh? my God. Oh my God. Okay, I'm almost through. So, good. Now, now we have distinguished I and J. Okay. So now I want to say use the W. That is the zero set of the J. Okay, let's check. That's what we had. Good. Right. Good. So okay, if I want to be detailed, so F is in I of B of J. Okay, and this is by the Nullstellensatz. This is the radical. Here is the Nullstellensatz. The Nullstellensatz gives this. Okay, so this means there is some natural number n. So that's F to the M is in J. So we know what is the radical of ideal. Okay, so this is the non-trivial ingredient in the argument. Okay, so but F to the M only depends on the last variable. So this is also here. Okay. So I see, okay, what do I want to show? Yeah. Yeah. So maybe, okay, this is actually not necessary, but why not write it? So okay, F is in the vanishing ideal of the zero set of JL. So I have shown actually what I wanted to say. This F vanishes here. I have this. So if you this arrow here is in a way the trivial direction of the Nullstellensatz. So it's the proof, and if you are a bit puzzled, I understand because I'm aware I did not properly explain all the basics. But I think with some work you will be able to follow the steps. Okay. Okay, maybe there are questions here. Maybe you can also ask next time after looking at it. And you can also ask Marco if you attend the exercise.
About the last implication?
This one, right. Yeah, because you see, okay, if I want to be formal, because this, okay, let me add something. I can also apply the Nullstellensatz here. Because if I'm here, I can say, aha, I'm in the radical, but say this is again here. This is again the Nullstellensatz. Now apply for JL. It's just a trivial direction, but yes. Formally it's now clearer. Thanks for the question.
Yes.
Okay, so.
Okay, I have to get used to it.
Yeah, well, this takes time. But you see, this is a nice theorem. This is a really nice theorem. Yeah. Maybe I do mark it in color because it's nice. Nice theorem. You see, why is it important? So maybe I... Okay, let's say you have a polynomial map. Okay, a function from k to the n to k to the m, where given by polynomials. Okay, then you want to understand the image. If the map is linear, you know, the image will be, say, affine linear, no problem at all. But here in this nonlinear setting, what will it be? Okay. We see already in this very little simple example that the image in general is not even Zariski closed. So the image will not be the zero set of polynomial system. But then we look at the Zariski closure, like the smallest set containing the image, which is a zero set of polynomials. And we want to compute polynomials describing this image. How can we do that? Okay, this is the task. Now, you see, in the theorem, the map looks very special. It's just a projection map. It looks very special. But it turns out with a little trick using the graph, this is actually the most general case. We will see later on when we do applications. This is the interesting case. It captures everything. Okay. So this theorem tells me how I can determine the Zariski closure of the image of the projection algebraically. Oh, we just of a subset of k to the n. Okay. The subset is the W. Where is it? Here. Yeah, it comes from an ideal. And the only operation I have to do on the ideal is intersect this. Where is it? Here. So the projection geometrically, which is geometric, corresponds to this. Intersect the ideal I with this smaller polynomial ring. Okay, so we have to see how can we compute IL, and what will happen? Very beautiful, right? How can we compute it? You assume you have a Gröbner basis of I, but now with respect to a good term order, which is called elimination order, Lth elimination order, and this would mean that if you have a term which contains one of the first L variables, x1 up to xl, this will be larger as any term in the remaining variables. So next time I give the formal definition. So special, these are elimination orders, like the lexicographic order would be good. Okay, x1 comes first and x2 up to n. And then we will prove, and it will be very simple, if I have a Gröbner basis of I with respect to such an elimination order, I get for free a Gröbner basis for the elimination ideal. So what do? From my Gröbner basis of I just select those polynomials that only depend on the last m minus l variables. I realize there is a to be L. That's okay. So this is extremely helpful. Okay. I will explain this next week. But this is yes. Question
about the formulation of this theorem. I think how we formulated that there should be actually I of V of IL, otherwise
I of
V of JL.
Sorry, now I'm very exactly.
So I of V of GL equals with the Zariski closure, because V would be polynomials that vanish, and then it should be I of. Or do we identify somehow?
So
I mean,
I think it's, I believe is okay. So I have my, I have my ideal J.
Yes.
It depends on, contains polynomials in n variables. I form the JL. So this is an ideal in the smaller polynomial ring, okay? When I write V of this, of course, the V now refers to, not to k to the n, but just, okay.
No, what I mean.
It's not the problem.
V was an ideal consisting of polynomials, right?
No. V is the zero set.
Another way around. Okay.
Zero set.
V
is for.
Yeah. Okay.
The V. Okay, it's confusing. V stands for variety. People, this algebraic, this Zariski closed set also is also called affine variety.
Oh,
Sometimes
I just confused that.
that is
I
the
see.
V.
I see.
Other people often, instead of V, people also like to write Z for a 0 set. Maybe that's more intuitive. I don't know. Okay. Other comments or questions, complaints? Okay. So I think this is quite interesting, by the way. So elimination theory was developed in the 19th century by actually, I think people in Berlin, Kronecker did worked on it. And yes, it has a very interesting story. Maybe I tell you next time about the story of elimination theory. Okay. Right. No more comments?
And could you sometime more give formal definition of Zariski closure? I mean, not by writing, but just by talking, because
Okay, you right.
Is
I
that
define what it means for a set to be closed, Zariski closed.
Okay.
Zero set of a collection of polynomials. But then if you have defined what are the closed sets, you also define what are the open sets. These are just the complements. And that's it. Then you have to verify the axioms of a topology.
Yes, but I mean, in the theorem now, we kind of used an implicit definition of closure because we never dealt, I mean, in the proof, we never dealt with topological notions. We just used, I mean, what did you understand under the closure of this set that we had to show?
Just a small interruption. Is it okay if I stop the recording? So maybe we can do it.
Yeah,
right.
Of course.
So I want to